To show that a vector field is not the curl of another vector field, we must first find a property of the curl that we can use to test vector fields. Here we note that it is possible to take the divergence of a curl as long as the vector field exists in 3 dimensions. This theorem states that given a vector field f equals pqr, the divergence of the curl of a vector field is equal to the dot product of del and the cross product of del and the vector field f, which is always 0. This is a useful property we can use to check if a vector field is the curl of another by taking the divergence of it and checking if the result is equal to 0. The proof uses the definition of curl and divergence and Clairaut's theorem. We have the divergence of the curl of f is equal to the divergence of the quantity r sub y minus q sub z times the unit vector I plus the quantity p sub z minus r sub x times the unit vector j plus the quantity q sub x minus p sub y times the unit vector k. This gives us r sub xy minus q sub xz plus p sub yz minus r sub yx plus q sub zx minus p sub zy. Rearranging this, we have r sub xy minus r sub yx plus q sub zx minus q sub xz plus p sub yz minus p sub zy. Clairaut's theorem states that the second derivative of a function is the same regardless of the order the derivatives are applied. In this case, it would show that r sub xy and r sub yx are equal. The same is true for q sub zx and q sub xz, as well as for p sub yz and p sub zy. Therefore, all of the terms cancel out and we are left with 0. In this example, we will determine whether or not f could be the curl of another vector field. We will use the divergence of the curl theorem to check whether there exists a vector field G where the curl of G is equal to f. First, we must check if f meets the assumptions of the divergence of the curl theorem, that the second order partial derivatives are continuous, and that f is contained in 3 dimensions. The domain of f is all of r cubed, and the second order partial derivatives are continuous. So this means that f meets the assumptions and the theorem can be applied. The next step is to take the divergence of f, which equals z squared plus x plus e to the z. This is not equal to 0. Since the divergence of f is not 0, and g is the curl of f, then the curl of the divergence of g would not be 0. There is no vector field G in which the curl of the divergence of G is 0, and the curl of the divergence of any vector field must be 0. Therefore, there cannot be a vector field G that results in the curl of G being equal to f.